Our final presentation, ladies and gentlemen, skin panel die market is largely untapped by ITRs. These are mostly imported, and in case you have plans to manufacture skin panel dies, this presentation is meant exactly for you. We have with us Mr. Martin Heckmann, Development Engineer, LÄPPLE Automotive. Martin graduated in mechanical engineering with a focus on metal forming technology from the University of Stuttgart. His professional career includes, amongst other things, positions in the technology development of tool and die companies. Since 2015, he works as a development engineer for LÄPPLE Automotive at the Heilbronn headquarters. His fields of activities comprise the development and testing of novel materials, forming and joining processes, as well as press die technologies. Ladies and gentlemen, Mr. Martin Heckmann. Can we have the LÄPPLE on? Yeah. Sorry. Yes, sir.
Namaste. Thank you very much for your kind introduction, Everest. Thank you very much to Tagma for the invitation. It's a great honor for me to be able to speak to you today about critical aspects of skin panels, and I'm glad so many of you are still here to share a little bit of knowledge on that specific topic with me. Anyway, it's a highly complex topic. We will be able to scratch only on the very surface of it. Okay. For a start, please let me briefly introduce our company, but I promise I cut myself short. At first, as you see, the original LÄPPLE company dates back to 1919. That means this year we have a major celebration coming up. Today, the LÄPPLE group of companies consists of 4 members. Fibro, that you all know as your preferred supplier of standard parts and rotary tables, also present here in Pune with strong manufacturing capabilities and an excellent team. Then FLT, specializing in automated production facilities for engine, drivetrain, as well as body in white components. Our training center, and eventually LÄPPLE Automotive, which is my employer. We operate 2 plants in Germany, one in Heilbronn, one in Teublitz, where we specialize in pressed parts and assemblies for passenger cars and commercial vehicles. Our press shops, we run mainly hydraulic presses and servo-mechanical transfer presses. Annually, we process approximately 80,000 tons of steel and 13,000 tons of aluminum sheet into structural parts and skin panels in the large to extra large segment, one could say. Our body and white shops, they produce complex assemblies using state-of-the-art joining technologies. For example, a huge variety of doors and closures to various customers, mainly in Europe. We deliver for small series to high volume production. To my personal dismay, I must admit that like 8 years ago, we traded off our internal tool and die department. That is where I made my first experiences in sheet metal forming or in tool and die, so that hurt me a lot. Anyway, today we are pursuing a global die sourcing strategy. That means we're buying dies from all over the world, referring to India or referring to Asia. We are mainly looking at China and Korea. Like, for example, we have a collaboration ongoing with Xinjiang for several years already. But when it comes to India, I must say that is still work in progress for our buyers for various reasons, but maybe this event can help a little for bridge building so that in the future we will do more business with India as well. So now to the actual content of the presentation. When we speak about skin panels, we are of course looking at fenders, sidewalls, roofs, door and closure outer panels, but also at structural parts with visible surfaces, such as, for example, A-pillars. They all have their characteristic features, and very often OEM-specific design attributes also play a role. Generally speaking, you could say the roofs are the easiest to manufacture, whereas the fenders, they usually give us big headache because a lot of different issues come together in those parts that make them so precarious. The main task in producing skin panels is the avoidance of surface blemishes that are visible on the painted car body. The notorious, for example, are flat spots, sink marks, waviness, impact marks from beads or die radius along styling edges or due to counterform onsets. Wrinkles, naturally, marks from die partitioning lines, marks of excessive pressure, localized pressure, or edge bulging. Sorry, I don't know the proper English word, and I couldn't find it in any dictionary, but maybe you can derive it from the flanging line of the part bottom left, where you have that special spring-back phenomenon after flanging. If you stone it, you have that longitudinal mark that looks a bit like a sink mark, long, slim, and narrow. Yeah. But also sliver from aluminium and zinc particles can cause surface problems when they come into existence during cutting operations, for example, and then get entrained in subsequent operations where they make impressions on the surface. Skin panel design usually starts with a thorough analysis of the curvature of the component, because many problems may already be rooted in the component's design. So flat spots and sink marks are prone to emerge in areas with diminished curvature. So the major, as a rule of thumb, the major curvature should not exceed 7.5 to like 30 meters, depending, of course, on boundary conditions like the minor curvature or the size of the affected area and other things. Yeah. Curvature transitions, such as displayed on the right-hand side, they imply an inherent flat spot, basically, particularly when the curvature in the other direction is not very pronounced. Also, the run-out of styling radii can give us severe headache in the tryout to make the visible appearance of the styling edges to be accurate, particularly when there's symmetric ones. Fortunately, there is a certain room for modifications in the design, while gaps and clearances and flush and aesthetic appeal, and that includes particularly the curvature, the smoothness of the curvature, they are sacrosanct. But in the panel center, the absolute dimensions may be negotiable with the component designer. So as long as the aesthetic appeal is maintained without any compromise. So, but if that is not possible to negotiate with the component designer, the critical earmarks must already be earmarked for subsequent measures in later on stages. Today, the extensive use of FEM software is already state of the art all around the world. FEM can also help to predict and prevent surface issues, but particularly when it comes to skin panels, we still have certain restrictions. Planar defects such as flat spots, they are highlighted, but by the numerical readout or the color scale, you cannot actually determine how severely the aesthetic appeal of the component is eventually affected. Also, zero radii, talking of tornado lines or talking of styling edges, cannot be represented like in reality at the moment. And eventually, If we apply spring-back compensation according to the conventional geometry-based method, we are losing our tangency. Our struck is going down the drain. As you can see, for example, on the right-hand side, this is a fender, isophote analysis or zebra analysis after springback of the surfaces, and you can see that severe distortions appear here due to deviations in developed length and surface content, surface area of the individual segments. So that usually requires painful reconstruction of the loft, something that we don't necessarily have to do on structural parts, for example. In order to tap the full potential of FEM when it comes to skin panels, we must spend increased effort on the modeling for the simulation. The simulations must indeed be done with the actual die faces and partitioning lines. That means, let's take a flanging operation as an example. In that case, we have, talking about a structural part, you would pick just like random, more or less random surfaces for your pad working from top down, whereas in skin panels, you need to use the actual partitioning line contour of your pad in order to be able to identify issues such as the edge bulging. Yeah? Also, in many cases, you have controlled forming of the flange instead of a simple bending, and in that case, you also have to model your counter pressure pad that works from bottom side up in order to get the additional tension into the flange that actually appears when flanging with a counter pressure pad. Yeah? And also, in many cases, one uses non-uniform engagement of the flanging die, like a shearing progression of the flanging die, of the flanging steel, typically from inwards to outwards. And in that case, the contour, the face of the flanging steel must be exactly the one that you have in your die in order to get an impression about the effects that it has. For example, when the flange is supposed to be hemmed afterwards in body in white. In any case, validation runs must be done with the final die phases before you go into the milling. When we are looking at risky areas concerning flat spots and sink marks, we've already seen that the readout is not 100% reliable. So really skilled assessment of the material flow and the strain distributions across several levels of your material are still indispensable. In order to minimize the risks, a plastic strain of at least 3% across the whole visible area must be assured. And as a rule of thumb, we use an addendum with an approximately 30-degree opening for that. Also, the stress states should be distributed as homogeneous as possible across the whole surface, and biaxial stresses are naturally preferred. Like whenever your minor stress goes into the compression domain, you are prone to get into problems with sink marks or with waviness. In some cases, stresses and strains can be positively affected by altering the part geometry. The depth of a door handle impression is a very good example for that. The actual depth can, in many cases, be negotiated with the customer, with the component designer, and therefore we can achieve a result that can help us to minimize those notorious Mickey Mouse ears, for example. Other surface blemishes appear due to contact of your tool with the sheet. Typically, we have the mark of the bead lines, so it is highly recommendable to locate the bead lines far enough away from the visible surfaces. And in terms of slip lines along the tornado line or along styling edges, one must strive naturally to balance the stresses on both sides to prevent that bent material from wildly sliding across your punch and creating the so-called slip line. In order to minimize such effects, you must consider the orientation of your part within your draw shell, or according to the working direction of the press, and also modifications of the draw depth and of the addendum may be helpful. One example we see on the right-hand side, we have a symmetrical bonnet panel with two styling edges, where it's literally impossible to get the stresses balanced. So what one can do is applying such a huge bulge, as shown below, that has a double effect. On the one hand, it prevents the bead line from and the die onset from sliding into the visible area. You see the trim line is like inside the bulge, and also we achieve the effect that the bending across the styling edge only comes at a delayed stage in the process, and therefore we prevent it from becoming an actual slip line. Naturally, such measures increase the blank size and hence the material cost. However, in general, the designer always strives to form all visible areas in one single operation to prevent any possible marks from subsequent operations. Wrinkles are nasty. Yeah? So even if your FEM simulation shows you in the lower dead point that everything is stretched out or iron flat, on the physical part, still marks may remain. That is particularly true when it comes to aluminium. So the process engineer assesses wrinkles at all stages of the drawing process, from the closing of the blank holder to the forming of the beads up to like the very end of the drawing process. It requires quite some experience to determine critical wrinkles from uncritical wrinkles that may disappear during the process. But since wrinkling is always a metastable, a more or less spontaneous event, it's very hard to predict and always poses a risk. Also, it is recommendable, particularly for larger parts, to provide support of the blank to prevent it from sagging into the blank holder opening and subsequently producing a material overshoot that may lead to wrinkling. Naturally, the blank holder surfaces are preferably fully developable, or at least consist of individual developable segments. And again, changing the part orientation may be required to achieve a beneficial, advantageous punch engagement that minimizes the risk of wrinkles or eliminates it completely. So before we start milling before we start the actual milling, let's have a look at our die phases. Local die phase adjustments can help to substantially decrease the spotting effort in the tryout. Such modifications are, for instance, edge subtractions to counteract this edge bulging. Others are spotting allowances in areas where grinding efforts are expected, or overbending or overcrowning or localized pressure may become necessary to form a proper die, to form a proper skin panel naturally. On the other hand, recesses reduce the grinding effort in non-shaping areas and opposite allowances, for example in upper dies where flat spots are compensated by overcrowning. You can see a few of the examples on the right-hand side, like when we look at the door handle impression, you have a recess, you have a spotting allowance in on the punch to overcrown to compensate for sink marks, and you have recesses in the upper die to minimize the grinding effort in that area. Another example would be deliberate spotting allowances left and right of very, very sharp styling edges, where you know you can form that zero radius only not by drawing or bending, but only by forging, by cold forging in the lower dead point. And instead of like spotting the whole die until you have the hard pressure right there where you need it, you start with a narrow area left and right of the styling edge that you gradually reduce until you have the pressure pattern that you want to have, and then you spot the rest of the die accordingly. When it comes to the actual die design, adherence to standards and guidelines play an even bigger role as in structural parts. Well, we all know that customer requirements can be a pain in the ass, and however, please don't consider customers' design standards as a sort of harassment or so. Please bear in mind that they usually contain the long-standing experience of the press shop with such dies in a condensed form. So yeah, it does make sense to strictly adhere to them, because that is the basis for future operationability and maintainability in the overseas press shop of the customer. Maintainability in particular calls for standard parts with proven reliability and global availability. In the past, we've had quite some issues with dies featuring, for example, self-made cams or improvised, non-standardized pressure pins. And after the first cycle of maintenance, we found that we had to do a full new cycle of die spotting in order to get the pressure pattern right again and to produce Class A parts. Well, this is regarding concerning the standard parts. This is particularly important for skin panel dies, because there we usually operate in a rather narrow process window to get our things right. Yeah. Once the die has been cast, milled, and assembled, the tryout starts. The tryout accounts for approximately 30% of the cost of a skin panel die set, and it always implies a certain planning uncertainty. Therefore, we must always strive to minimize the tryout effort by stringent front-loading. That means that at no stage of the engineering or manufacturing process we must pass on unresolved issues downstream. To master that last stage, a team of skilled, experienced, and motivated toolmakers is absolutely necessary. At first, they need to meticulously spot the die to a condition where the outcomes are identical to those in the simulation in terms of pressure pattern and particularly die draw-in, blank draw-in. That is usually a very good starting point, because then you have pretty much the same situation as in your green simulation. However, those guys, they do not only need to be able to grind and weld, they must also thoroughly understand the laws of material flow, for example, and they must be able to read measurement reports and to understand clamping concepts and they must be able to understand the effect of clamping onto the measurement outcomes. And from that, they are able to derive compensation strategies, correction strategies, all along the die set to get to an immaculate part eventually. Yeah? In order, if you find deviations in your production process, then you must determine the sources, of course. Yeah? Forming analysis can be a very good tool, and you can compare the strains that you have in your panel to those that you have in the simulation. And in a similar way, you can use reverse engineering, like scanning your actual die faces after grinding and all that, and feed them back into simulation, run additional simulation, and look for the root causes of the problems that you have in your physical die. Once the process is stable, it must also be made robust against the typical variations that we have in like sheet thickness, material strength, and friction. Therefore, we run the tryout usually against varying input parameters such as blank holder pressure, blank holder spacing, distancing, and so on. And that helps also to facilitate the handover from tryout press to production press. That helps a lot, and it also anticipates the effects of like later on hardening, coating of certain tool elements. So, coming to a conclusion, we can state that for skin panels, aesthetic appeal is number one priority. That refers to surface curvature, as well as to tolerances affecting gaps and clearances. The provision of Class A surfaces, however, comes at a price. Engineering and tryout require a certain amount of extra effort, and often we need larger blanks. That means we have higher material cost, lower material usage, and eventually your dies become more complex and more expensive due to an increased number of cams, for example. So in the skin panel business, we are confronted with ongoing challenges. Currently, lightweighting is one major topic. Lightweighting leads to an increase in aluminum application and a decrease in sheet thickness, and both makes life very hard for us because both lead to an increased sensitivity of the process and sensitivity of the surface quality and spring back and so on. Skin panel designs are also becoming more and more precarious. A current example is the Porsche Macan frontlet that you see top right. Yeah? We can see 6 potential slip lines. We see 2 huge openings in the panel surface, and we see a draw depth that includes half of the wheelhouse. So that is actually a very demanding challenge. Yeah? So some of that we can compensate or with advanced numerical models. Like a lot of progress is being done on that side, so we can squeeze out the last bit of formability out of the steel or aluminum that we have. But more than ever, we need process engineers and tool makers with skills and a high level of ingeniousness. Yeah? Despite all technical progress, skin panel dies will remain the distinguishing mark for top-class die makers. So, then thank you very much for your attention, and again, thank you for having me here.
Thank you. Thank you very much, Martin. And sorry for the little mishap in the beginning. Right now, we would like to invite Mr. Pramod Bhandari, DGM PE Planning and Services, Tata Motors, to step up on stage to hand over a memento to Martin Heckmann. Ladies and gentlemen, Development Engineer, LÄPPLE Automotive, Mr. Martin Heckmann. Please get your hands together as Mr. Bhandari hands over a memento to Martin.